Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
All right. So, hope you all had a good holiday yesterday. Didn't waste the day like I did. I had about 1,000 things I needed to do, and of course I did what normal people do when you've got too much to do. I did none of it. I procrastinated the entire day, which wasn't good. So anyway, I hope your day was more fruitful than mine. All right. Okay, so talking about time series, and last week we talked about the trend part of a time series, which is basically where the series is going, leaving aside the wiggly behaviour, because you can see in this series you've got a lot of wiggles. But the wiggles are there every year, and we're going to deal with them separately. So you kind of got to ignore the wiggles and sort of see where the series is basically going. And last time we looked at a couple of different approaches. We have a low S curve, which is the red line. And remember, low S ignores, more or less, extreme points. So it's very good at dealing with the wiggles. It doesn't follow them up and down. It can basically carve through the main path of the data. So you can see that sort of slides up, crests, comes down, maybe tails off at the end. But we realise that low S doesn't give you good ability to predict because you don't get a formula, right? You really would like a formula. So we looked at polynomial type models, and you can see for this particular data, a polynomial which sort of has those couple of turning points, which would be a cubic, goes up, comes down to a trough, and then starts to rise again. Seems to fit the data pretty well, and seems to follow the low S curve pretty closely. So a cubic polynomial might be the way to go. And polynomial models are good because they give you easy way to predict. If I want to predict at a particular time, I just plug that time into the polynomial and I'm good to go. And there's a couple of caveats. The first caveat is don't fit really high order polynomials, so fifth order or higher would I'd say probably be something you should never do. Think hard about fourth order. Up to 3, probably okay. Second comment to make is that if you are going to predict using a polynomial model, just be aware that that thing's going to degrade rapidly once you get off the edges of the data. And no one wants to predict backwards, but everyone wants to predict forwards. After this, 1990, right, it's going to start to rocket up, and the data's probably not going to go with it. So predictions in the short term are going to be okay, predictions in the long term are probably not. At the end of the last lecture, we looked at a differencing in order to deal with polynomial terms, and the comment was that a first order difference will remove the highest order polynomial term. If you take differences twice, you'll therefore remove the top 2. If you take differences 3 times, you'll remove the top 3. So if you believe that your data follows a cubic, removing those top 3 polynomial terms will get you back to a flat line. All right, so differencing is a productive way to go. In R, if you take first differences and you plot it, you get this. And I'll put a low S curve through that. Okay, the command to do that is plot diff of Z, and then lines of low S of time Z and diff of Z. Now, if you do that, what you'll notice is you get an error. X and Y lengths differ. And that's because when it takes differences, it's got to go x1 minus x0. Oh, there is no x0. So it drops the first one, right? Has to. Can't do anything else. There's nothing available to difference with. So that differenced series is of length 1 less than the original series. So what I had to do was go lines, low S, time of Z, and then remove the first element, right? Because it's not present, right? So that's the difference series. You can see it's pretty flat after one difference, okay? If I wanted to take differences twice, this is how I do it. I go diff of Z, comma 1, comma 2. So let's take first differences of Z twice. So the 1 means you're taking first differences. That is Z minus its immediate past, right? 2 there means do it twice. So diff Z1, 2 takes first differences twice, okay? Again, if I just remove the first one, the series don't match up in length, I have to remove the first two. And again, it's because when you take first differences, you've got a difference against something, and there is no x0, and then in the difference series, there is no diff of x0. So you have to take the first two off, and the plot looks like this. And you can see, again, pretty flat. There's a bit of a curvature to this, but not too bad. And then finally, to take differences, first differences 3 times, diff z1, 3. When you plot it, you have to remove the first 3. Okay, so not rocket science, but there we go. And that's the result.
What is the meaning of if you take the third difference? How can you explain it?
Ah, it's a good question. It's a good question. So let's explain that. So diff of z is z at time t minus z at time t minus 1. Okay, so that one's easy. All right. Oh, I should have put a hash in front of that so that it didn't try to do it. Okay, diff z12 is equal to, well, it's diff of z at time t minus diff of z at time t minus 1, okay, which equals diff of z at time t is z of t minus z of t minus 1, right? That's the first term. Minus diff of z t minus 1 is z at time t minus 1 minus z at time t minus 2, okay? You can see what's going to happen here. So you get zt minus 2 times zt minus 1 plus zt minus 2. Okay? So you can write first differences twice in terms of the original z's just by working through the algebra. It won't surprise you to learn, or maybe it will, diff of z13 is equal to, now you can do all the algebra. I've done all the algebra sometime in my life. It looks like this. Okay, you can write diff of z13 in terms of the original z's. Okay, so that's how you do it. Now, if you want to use this for prediction, you got a bit of pain coming, because you want to predict z at time t, but if you don't know what z at time t minus 1 is, you're going to have to predict that first. And if you don't know what z t minus 2 is, you're going to have to predict that first and recurse. So this is something that works beautifully in Excel. Excel does recursion really easily, right? You know, you just double click on the corner of a cell and it fills down and it works it all out on the fly. So Excel does recursion well. So probably the first time and maybe the last time in the course you'll hear me talk about Excel doing something well, but it does recursion really well. R does not do recursion well. You'd be in a world of pain. You'd have to work all the interim z's out in order to do it. So using differencing makes prediction, it's not hard, it's just tedious, because you've got to calculate all the interim z's that you don't know. So if you just want to do next step prediction, differencing's fine. If you want to predict 2 or 3 time points into the future, you've got to work out all the interim predictions and then fill back in, which Excel will do in a heartbeat. R won't do it in a heartbeat. Okay, unless you've got a slow heartbeat. So that's how differencing works. What would I use? Well, look, simple is best in my view. Polynomial models, I think, are probably the go-to, unless there's a good reason to use differencing. Now, we'll see a little bit later, probably tomorrow, a good reason to use differencing sometimes, okay? But for the moment, you can think of polynomial approach and differencing approach as alternatives that do pretty much the same thing, okay? There is a slight difference in terms of the way you'll interpret them, and that has to do with how you have to do predictions. Now, have a look at this last one here. That's pretty flat. You can see the low S curve that goes through there is pretty flat. And that line, the height of that line is your model, right? So your model would be, in this case, diff Z13, which is that complicated thing involving the z's, right? So it's just that. That equals a constant. And that constant would be mean of diff Z1, 3. Okay, you take the mean of that, you'll get the constant. And we can take the mean of that really easily. You just go mean diff Z1, 3, and it's 7.4. So your model would be ZT minus 3, ZT minus 1 plus 3 ZT minus 2 minus ZT minus 3 equals 7.4. That's your fitted model. And if you wanted to do prediction, you've got to back it all out, right? So it's not easy. Okay, if you want to do one-time ahead prediction, it is easy because you know what ZT minus 3 is, you know what ZT minus 2 is, you know what ZT minus 1 is, you've got those numbers, so you could just plug in. Further out, you've got to backfill. So that's trend modelling. Trend modelling is pretty easy. It's just like regression with time as the x, so easy peasy. And if I do fit that cubic model, which I've done, then I can look at the residuals from that cubic model and I get a residual series. Now that residual series does not look like a regular error model for a regression, because in a regular regression you don't have the wiggles, right? So we've dealt with the trend part, but we haven't dealt with the wiggly part. And that's what we need to deal with next, is the wiggly part. All right, now, we're going to fit a really simple model for seasons, okay? We're going to fit a really simple model for seasons. Our really simple model is going to say that seasons are flat internally, right? In other words, I'm just going to fit a constant for each season. Now, think through this problem, right? In winter, sales are low. So we're just going to fit a low number for winter. And in summer, sales are high. So we're going to fit a high number for summer. And then spring and autumn are in between, so we'll fit different numbers for each of them. Now, this is a really simple model, okay? It is by no means the only model you could fit for seasons, but it has the advantage of being really simple. You'll have one parameter per season, and it's going to be like winter's low, summer's high, autumn and spring are middle somewhere. Okay? Now to do that, we need to set up what's called a factor. Okay? So here's how you set up a factor. What we do is we work out in which season each data point occurred, and then we create a vector that just lists the seasons in which each data point occurred. Now, this data set started in the third quarter of 1974. So the first data point is in season 3. The second data point's in season 4. Then you have 15 full years of data, right? What's a full year? 1, 2, 3, 4. So you repeat 1, 2, 3, 4, 15 times. Then your series ends with first season, second season. It finishes in the middle of 1990. Okay? So it starts in the third quarter of 1974, that's 3. 3, 4, 15 full years. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. I said that 15 times. 1, 2, 3, 4. Okay? 1, 2. So all I'm doing is just creating a big old vector which contains the season in which each data point is. And I'm feeding that into a function called factor. So what that does is it creates in R what's called a factor, a level for each season. Okay? So we do that. Okay. Now, the next two lines are just to check that I got it right. So I'm just checking that I've got 16 full years of data. Okay? So that last thing there is just a check. You don't have to worry about that. But that's how you set up the factor. Okay? Now let me show you what this factor looks like. Just type V. It's going to spill to the screen. It's a matrix. It's got 3 columns. Okay? You'll notice the first column that corresponds to season 1 is missing. This is how factor works. It's a baseline, right? So your first season is baseline. Then your second season is on top of the first one, third season on top of the first one, fourth season on top of the first one. This is how you fit a factor in R. The reason it's a baseline is your model has a constant in it, an intercept. So that soaks up the baseline. So season 1's baseline, then you go seasons 2, 3 and 4, which are extra constants that go above and below the baseline, depending on which season is the baseline. All right? Now I'm going to fit the model. Easy to do. So here's my time series, Z, and I'm going to give it a cubic trend. So I'm going to give it centred time squared, and centred time cubed. Remember last time we had to centre time in order to fit the cubic. It wouldn't fit otherwise. And then I give it this factor, V. So I just add V to the model fit. So let's go ahead and fit the model. Okay. And now I'm just going to type fits and you'll see what the model is. So there's the model. Okay, I'm just going to go options digits equals 2 because too many digits. Okay, there's fits. Okay? Right, your intercept is 1576. Your coefficient of centred time is minus 2.82, of centred time squared minus 1.45, of centred time cubed 0.24. Then, for season 2, minus 68. Right? Season 3, minus 46. Season 4, 183. So let's try and write down what the model is. So here's your model. It says that alcohol sales are equal to 1576, I'm going to leave off the decimal points here where I can, minus 2.8 times time minus 1982. Remember we centred time at 1982. Minus 1.45 times time minus 1982 squared. Okay. Plus 0.24 times time minus 1982 cubed. Right, so there's my cubic. Now, season 2 is winter. Right, season 1 is autumn. That's the baseline. So we get minus 68 times an indicator that I'm in winter, minus 46 times an indicator that I'm in spring, not spring, plus 183 times an indicator that I'm in summer. And that's my model. Okay? You go, what happened to autumn? And the answer is, that's baseline. That's in your constant. Okay? So if I wanted to do a prediction for autumn of 1993, all right, what would I do? Autumn of 1993, so let's think about it. Autumn 1993, what's that? That's 1993.75. 3/4 of the way through 1993. So that's your time. Okay? So what I do is I come to my model and I go, okay, in autumn 1993, I pick up 1576, right? Minus 2.8 times 1993.75 minus 1982, right? Minus 1.45 times 1993.75 minus 1982 squared. That's the second term over here. Then I do the third term. It's not winter, so I don't pick up anything for the winter term, right? This is an indicator of winter. It's a 1 when it's winter and it's a 0 when it's not. It's spring. So, nothing. Okay? Oh, sorry, it's autumn. It's not spring either. It's not summer. So you don't pick up any of these, right? None of these appear. You just get that cubic bit. That's what happens in autumn. Now, if I asked you to predict for winter, what would I do? Same thing. 1993 winter would be 1993.5. Sorry, season 2. 1994.0, right? Winter. Okay? Plug that time in here, here, here. Now you pick up this term. Okay? But you don't pick up spring and you don't pick up summer. So it drops 68, right? Drops 68. So in spring, you just pick up the baseline, which is your intercept. Sorry, in autumn. I've got to get this right. Autumn. Season 1. Right? In winter, you pick up the winter term. In spring, you pick up the spring term. In summer, you pick up the summer term. That's that. Okay? So it's a really simple model. And you can do predictions based on this model. All right, now, let's have a look at these seasonal series. So what I'm doing here is I'm going to construct 4 plots, once for each season, okay? So all I'm doing here is I'm going to plot all of the summers, all of the winters, all of the autumns, all of the springs. Let's go ahead and do that. So we do this, okay. So I'll just show you the 4 plots. Okay. First, second, third, fourth. Okay. So all I'm doing here is it's a plot of every single, what's first season is autumn. Autumn, winter, spring, summer. I'm using the same axes for each one, as you can see. So autumn's sort of middle. Winter is low. You notice how the line is at the bottom of the plot. Spring, higher. Summer, highest. Okay? I'm just plotting every 4th point, right? So the R code to do that is here. Okay, it's a little bit complex. The reason it's complex is because the series does not start at the beginning of the year. It starts halfway through the year. So you've got to do a bit of messing around. That's why I have to put missing values at the start, right? But basically you're picking out when it's each season. Okay? So that's the seasonal subseries. So a really simple model for seasonal, just a constant for each season. Okay? So the steps are simple. Step 1, create your seasonal factor. Okay? Step 1, create your seasonal factor. In other words, create a vector whose content is the season in which each data point appeared. Okay? Then, step 2, fit the model. The model has the polynomial bit you had in the first part, that's your trend. Then you just add that factor at the end, that's your seasonal. Okay? Fit that model. Have a look at the model fit, and you can write down the model really easily. All right? That's it. Now you can plot the seasonal subseries if you want. You don't have to. But it's pretty easy to do. So this is the way you can fit a seasonal model. Now, like I said, there are lots of models for seasonal behaviour. This is a really simple one. It just says that each season is somehow homogeneous. Winter is low, summer is high. The other 2 seasons are in between, but constant within a season. Okay? Really simple seasonal model. So we're going for simple here. Okay? Now, the next thing to tell you is that R has a really nice function that lets you explore seasonal and trend behaviour. And that function is called STL. So this is kind of an automated way to do season trend analysis. So that function's called STL. There is one gotcha. STL will only work when your series has frequency bigger than 1. In other words, measured multiple times per year. Okay? It will only work when you've got seasons. Now, not every data set is seasonal. Okay? Not every data set is seasonal. If you've got annual data that's measured once per year, you're not typically going to have seasonals. Doesn't mean you can't have periodic behaviour, you can, but you're not going to have seasonal behaviour typically. Okay? So data is usually measured monthly or quarterly or semi-annually, so twice a year, or annually. Right? These are the typical kinds of numbers. When data is measured monthly, frequency is 12. When data is measured quarterly, it's 4. When it's measured semi-annually, it's 2. When it's measured annually, frequency is 1, and STL won't work. Okay? Now we can trick it, we will in a minute, I'll show you, but generally speaking, you can't use STL unless your seasonal component is well defined. All right, so let's run it. Okay, the command is simple, STL. STL stands for seasonal trend low S. Seasonal trend with low S. That's what it means. Okay, you give it your series Z. then you need to give it two things. S.window equals periodic, that says fit a seasonal effect. Periodic means repeating, right? Then you give it this thing T.window. This is your trend window. It's using low S to fit a trend. And you need to give it a window width in low S that's big enough that your trend doesn't follow the wiggles, right? Typically, what do I choose here? I choose a number that's about 2/3 the size of my length of data. So here I've got 64 data points. So 2/3 of 64 is 40 odd. So I chose 41. You choose 40, 42, doesn't matter. As long as it's a biggish number, to about 2/3. And remember, low S uses a window in typical regression contexts where F is 2/3, right? So I'm just using that 2/3 rule. So take the length of your data, 2/3 of it. That'll give you a window width you can use. Okay? So once I do this, once I plot the output of H, this is the plot you get. It's really pretty. Okay? There's my original series. That's the original alcohol data. The first thing is the seasonal effect. That's just the wiggles. Just the wiggles. Okay? It looks flat apart from the fact that it wiggles. Okay? There's my trend. Looks like that low S curve we had before. Right? Goes up, peaks, troughs, and then slowly rises. This last one is what's called irregular or residual, and it's basically what's left over after I fit the seasonal and the trend. All right? So that's what STL does. Now, I use STL really just to get a hint about what's going on in the series, right? Because it's using low S to fit all these components, it's not particularly useful for prediction. You don't get formulas out of it, so you can't really predict using it. But I use STL when I can as a guide for what I should fit later on using regular models, right? So when I look at this STL output here, I see, oh, you know, that trend, it looks kind of cubic, so I'm good to go with a cubic, right? And I look at that seasonal part and I go, yep, that looks pretty good. A constant seasonal looks like it's going to work, right? Because there's a regularity to those wiggles that gives me some confidence that, you know, in summer it's sort of flat across the top, and in winter it's sort of flat across the bottom, right? So I can fit constants to each of those seasons. So I use STL as a bit of a check that the model that I'm fitting is okay. The other thing that STL gives you is you can produce what's called a month plot. And this is a plot of the 4 seasonal effects. So the command's pretty simple. It's month plot, and I give it the output of the STL command. Okay? And then this is my Q1 effect. So that's autumn. Q2 is winter, so you can see I get a flat line that's low. Q3 is spring. Q4 is summer, that's high. Okay? So it kind of gives you a bit of a hint as to what kind of model you are going to fit if you fit a constant seasonal model. Okay? That is a constant for each season. So that's how I use STL. So that's a pretty cool tool, and it's really good as an exploratory tool, right? To just give you a hint as to whether you're on the right track or not. Now I want to show you a couple of things. I'm going to go back and refit the STL, but I'm going to leave the trend window to be small, or at least leave it out, T.window. It's going to just use the default, right? Look what it does. See how bumpy that trend is? That's using a low S smoother on the trend component, but with a really small window. That's why I had to go T.window equals 41. If you just leave it as the default, it uses a small window, you get a really bumpy trend. That's terrible, right? It overfits it to hell, okay? So that's why I've got T.window equals 41. It's just to give it that better look. And look, I can... 41, the number 41 is about 2/3 of 64. That's where I got it, right? Look, if you use 45, you're not going to see much difference, right? So it's just a number that is about 2/3 of the data size. If you make it too big, you'll squeeze out all of the structure, right? So let's make t.window really silly, 1,000. See how all the structure disappears? I've smoothed it all away, right? And if you make t.window really small, you'll get something silly again, right? So it's a low S smoother. That t.window is telling you how smooth to make it, right? And that 2/3 of your data size is about a sweet spot. Okay, that's why I've got 41. So if your data set had 100 data points in it, you'd use about 60. If your data set has 1,000 data points in it, you'd use about 60, 600, 600 or 700, right? Use that 2/3 as your guide. Okay, so that's seasonal. So really simple model for seasonal. And look, again, let's be clear, there are more complex models you can fit for seasonal effects, but we're going to stick with a constant seasonal model just because it's simple and it deals with the structure that we've got. And now, I've got this model, right? I called it fits. You can see it's got all these different components. Got an intercept, which is your baseline for autumn. You've got coefficient of time, coefficient of time squared, coefficient of time cubed. You've got an indicator for winter. You've got an indicator for spring. You've got an indicator for summer. Okay, that's my model so far. If I look at this model, fit, right, so there's my original data. Oh, that looks so weird. I must have, oh, let me just scrub the thing and let it fill the plot. Let's do that again. There it is. There's my original data. Here's my fitted model. Okay, it's the dotted line, right? So here I'm just fitting time of Z versus my model, right? The fitted values from my model, okay? And I'm putting that in as a dotted line. Now, if you have a look at it, can you see the dotted line well enough there or not? No? Let's do it again with a red line. It might be easier to see. So I'll plot the data. Then when I put the line on, I'll make it LTY equals 1, colour equals red. By the way, the fitted values, there's a couple of ways you can get them. I've constructed them manually. You could just go fitted of your model. Okay, that'll work too. Okay, so, because RLM supports the fitted command, so rather than building your fitted values manually, you can just do that. All right, so let's have a look at it. So the black line is my original data, the red line is my model fit, so that's a cubic trend plus a constant seasonal, and frankly, I think we did pretty well, right? That looks pretty good. Certainly, the red line seems to be tracking the data pretty well. It misses a little bit here. It misses a little bit here, but everywhere else, pretty close. Why does it miss? Well, maybe you had a cold winter, right? So sales dropped a little bit, okay? Your model can't necessarily account for that, that's just noise, okay? And so, but otherwise, it's a pretty decent model. If someone said to you, predict alcohol sales in a particular time, you're going to do fairly well with this model. You can see it tracks the data pretty closely, okay? All right, now what about the residuals from this model? What's left? So let's have a look at those. So this is a plot of your time versus fits dollars resid. So this is what's left after you fit your seasonal model, okay? So there should be no structure left. Now, this is where the rubber hits the road a bit, because this does not look like random noise, okay? This does not look like random noise. It should be random noise, but it's not. Why? Well, let's talk about its features. First of all, it's got mean zero, because I fit all the structure. So this is centred around zero. You see I've put a flat line at zero there? Okay? But what should random noise look like? Let's plot some random noise. Random noise should look like random normals with mean zero and some variance, okay? So let's just plot 64 random normals with mean zero and some variance, okay? Type equals B. That's what random noise looks like. Let's do it again. Random noise, random noise, random noise, random noise, random noise, random noise, etc. Okay, so just have a look at them as they go past. I'm doing a lots. Okay, had a look at all them? All right. What does our data look like? Does that look qualitatively the same or different? Looks different, doesn't it? What's different about it? What's different about it? In words, just common English words. What's different about it? All right, let me ask you a question. Is it as wiggly as the other one? No. It looks like more like mountains, right? Random noise wiggles a lot more, right? That's because with random noise you've got independence. So from each one to the next one, as you move along, you've got an equal chance of going up as down, okay? So that's going to produce a wiggly plot because as you move along, it's got roughly 50% chance of going up, 50% chance of going down, so it's going to go down half the time, and so it's going to wiggle a lot, up and down, up and down, up and down, okay? The series I've got here doesn't seem to do that. It's not wiggling a lot. And the reason it's not wiggling a lot is that when it's on the way up, it tends to keep going up. That's correlation. If xt is correlated to xt minus 1 with a positive correlation, then if it's on the way up, it's going to tend to keep going up. So you get these kind of mountain-like structures where it's sort of tends to head in one direction for a little while. Then when it turns, it tends to head in the other direction. So the way to think of it is in random noise, you've got a 50-50 shot of going up as down as you move along. So it wiggles a lot. If you're correlated, it might be a 70-30, 70 up, 30 down. Well, if it's 70-30, then when it's on the way up, it's going to tend to build up. It can turn. It's got a 30% chance of turning. Once it turns, it's going to have a 70% chance of staying down too. So it's going to go down a little bit further. So you get this kind of picture. Okay? A really simple way to check out whether these are correlated is to take, so this is my residual series from my trend seasonal model, is to take my residual series and plot it against its immediate past. So I'm plotting item 2 through 64 of my residual series against items 1 through 63. So I'm plotting xt versus xt plus 1. Okay, so let's have a look at this plot. That's xt versus xt plus 1. Okay, what does this look like? Does this look like random noise? No. It's going up. Would you put a straight line through this? Why not? Right? Let's put a straight line through it. So, this says to me that xt is linearly related to xt minus 1. That's correlation. But it has a special name because it's relating x to itself. Autocorrelation. Exactly. All right? Autocorrelation. So, the series you get out of time series after you fit your trend seasonal are autocorrelated. They're not independent. Okay? And that's a big difference. All right. So we need to deal with that. Now, this one here gives us a hint about how we can deal with it. Right? So this plot shows that x at time t is related to x at time t minus 1. All right? So, and in fact, when we look at it, it looks like something like this. xt is equal to some constant a plus some constant b times xt minus 1. We saw a straight line here, right? So xt looks like it's linearly related to xt minus 1. But these are residuals, so a is 0. They're centred at 0, right? So your intercept's going to be 0, okay? Both series have mean 0. So the model we're going to fit is this. xt is equal to some constant times xt minus 1. Okay? Now that model has a name. That model has a name. In fact, I should be a little bit more careful because I haven't fit the model yet. So I've got to put plus error in. I haven't fit it yet. So that's the model that I'm going to fit. And it has a name. It's called a Markov model, named after a Russian mathematician, Andrei Markov. Or, alternative model, name AR1. AR, autoregressive, order 1. So those are the names that you give to that model, okay? AR1, or Markov model. All right, now, there is a restriction that we need to know about. The absolute value of the constant, has to be less than 1. Oops, absolute value of the constant less than 1. If the absolute value of the constant exceeds 1, the series explodes, right? So imagine the constant was 2. Then xt would be 2 times xt minus 1, which means xt plus 1 would be 2 times xt, which is 4 times xt minus 1. And it just explodes. So if the constant is bigger than 1, you get a series that explodes. Okay? So the constant is less than 1, and this is a condition for what's called stationarity. And stationarity is this condition for time series that describes the movement of the series. So a series is stationary if it has a certain property. Okay? So here's a definition. Series is stationary if, okay, now, hold on to your socks. The series is stationary if x at time t, x t plus 1 up to x t plus s has the same joint distribution, it's getting hard fast, isn't it, as any other subpart of x with the same length. So x r plus 1, comma, dot, 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 x r plus s. Okay, that's the definition of stationarity. Any sequence in the series of length s has the same joint distribution. Okay? Now, if you didn't do Stat 2001, you're probably looking at me going, joint distribution? What's that? So, we're not going to talk about that here because that's for a different course. We're going to do it in plain English. Okay? There are two things that happen for stationary series. First of all, they've got to be mean and variance stationary. So mean stationary means the expected value of x at time t minus x at time r has to be constant. Okay? The mean doesn't move. Okay? Variance stationary. The variance of xt has to be constant. Okay? Mean and variance stationary. The third condition is that the correlation between xt and xt minus some number a has to be constant. Okay? All right, so these are all mathematical things. We're not going to worry about them, so I'm going to tell you in just plain English what it means. First thing, a stationary series can't move systematically. So in other words, the expected value can't shift around, it's got to be constant. That's what mean stationary means. It means if you look at a stationary series, it should always buzz away around that zero line, right? Or sorry, some constant line, some flat line. Okay? Its variance has to be constant. That means, again, use the two fingers. As you move along the series, your fingers shouldn't get further apart. as you move along. Okay? And then it's got to be covariance stationary, which means its covariance from x now to x sometime in the past can't shift either. Okay, so what does that mean? What does that mean in really plain English? Because I'm still using all these mathematical words. In really plain English, what stationary means is, let's suppose I give you a series, right? I give you x1 out through x a million, okay? And I drop you somewhere in it. So I drop you somewhere in the series. And I ask you a question. Whereabouts in the series are you? Are you 2 along? Are you 10 along? Are you 400 along? Where are you? Right? Stationary means you don't know. Means you don't know. You look around, and the series is basically flat, no matter where you are, and the variance is basically constant wherever you are, and the covariance is basically constant wherever you are. So you're looking around and you're going, I don't know where you dropped me, right? I don't know where you dropped me. And you don't have a map, so you're stuck. Right, so stationary literally means no information about where you are in this series. You can't get information from the mean, you can't get information from the variance, you can't get information from the covariance. But there's still structure. The covariance doesn't have to be 0. In an independent series, which is automatically stationary, the same thing is true. If I give you an independent series of length 1,000,000 and I drop you somewhere in it, say I drop you at 0.6000 in that series, you can't tell me you're at 6,000 because there's no information to tell you whereabouts you are, right? There's no correlation either, right? This one is correlated, but the same concept holds. You still don't know where you are, okay? So that's what stationary means. It's pretty cool. Now, when you have a stationary series, you can fit a Markov model to it, okay? So we're going to do that. The first thing we're going to do, and this is going to be for tomorrow, so I'm going to stop in a second because this is going to take a little bit of explaining. We're going to fit the autocorrelation function and something that's called the partial autocorrelation function. These two tools are going to help me determine the covariance structure of my series, okay? And they're graphical tools. So that's going to be what we're going to start talking about tomorrow. I'm not going to start talking about it now because I'll just have to finish in half a minute and then tell you I'll pick it up there tomorrow and repeat everything. It's going to frustrate everybody, so we're not going to do that. So we're going to stop there today. And tomorrow we're going to pick up talking about these pictures and how you fit models using them. All right, see you tomorrow back on the other side. Oops. Yeah. 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 Yes.
So is this constantly decreasing?
Yep. Yes. Yep. So tomorrow we're going to talk about how the covariance cascades. Yeah. 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 Yeah, it is.
I mean the -1, so
Oh, yeah, yeah.
that one.
Where did I put it?
I think it's the beginning of the lecture, so
Yeah, it's up at the top.
sorry. Can I take some pictures?
There it is. Right there.
Thank you.
Yeah, go for it.
So this is what we like the original data minus the fitted.
Minus the
model.
fitted, minus the trend seasonal, yeah.
So it's not random noise. What's that imply?
Well, it's not white noise,
Yeah, it's not white
right?
noise.
So it's
Yes.
grey noise. So it's still noise, it's still got mean 0,
Yes.
but it's correlated. So it's autocorrelated noise,
Okay.
okay?
So what we down here, is it based on the residual or the original data?
A residual
The residual.
from your trend seasonal model.
Yes, and we call it AR1. AR1 is the original data. Is AR1.
No, your original data has a trend
Yes.
and a seasonal.
Yes.
Okay, so you remove the trend and seasonal.
Okay.
Cool. You remove your trend and seasonal, and then you fit the model to what's left. Okay?
But the model is also autocorrelated.
Yes. But what we're doing is we're parting it out. We're
Yeah.
dealing with the trend first,
So-
removing it,
Yeah.
dealing with the seasonal next, removing it, then what's left has all the autocorrelation in it. So we're sequentially
Yes.
taking out all of the components, all of the structural components. Now I've got to start walking back because I've got a meeting right after, but you can talk to me as we walk. So,